Hey everyone, so in this video we are going to solve today's contest, LeetCode Weekly Contest 502. So let's dive into the problem set. Here is the first problem, that is check adjacent digit differences. In this problem we are given a string s consisting of digits, and we need to return true if the absolute difference between every pair of adjacent digits is at most 2. Otherwise return false. The absolute difference between a and b is defined as okay. So let's iterate over all of the adjacent digits. So what I want to do is let's current, what is the current digit? S of I minus 0. And what is the previous digit? S of I minus 1 0. Okay, if the absolute difference between these digits is greater than 2, then we will return false. Otherwise we will return true. First sample test case is true, second is false. Great, so let's move to the next problem. Here in this problem we are given three integers L, R and K. An integer y is said to be perfect power of k, an integer y is said to be perfect kth power if there exists an integer x such that y equals to x to the power k. We need to return the number of integers y in the range L to R inclusive that are perfect kth powers. Okay, so this also looks very simple problem. So one of the brute force solution is we can iterate over all of the integers L to R, okay, and see if the particular element, particular integer between L to R is kth power or not. So simply we can count and return the total count, which are perfect kth powers. But I assume that L and R should be high enough such that the linear solution will not work here. We need to optimize it. Okay, so one thing is true, that if k equals to 1, then every integer between L to R is perfect kth power, right? Because the number itself to the power 1 equals to the number itself. And let's say if k equals to 2, then think of it like this: how many maximum numbers between L to R can be perfect kth powers? So what I am saying is, let's say we are given two integers L and R, and there are many integers between L and R, and we are also given k. And for the case 1, if k equals to 1, then our answer will be total integers between L and R, right? That is R minus L plus 1. Why is this answer? For any integer between L and R, x to the power k, that is x to the power 1 equals to x. So every integer is perfect power of itself. Let's say for k equals to 2, for k equals to 2, think of it like this: how many maximum number of integers can be the perfect kth power? So they can be root of maximum number of integers are order of root of r. Why? Because any integer to the power k, that is 2, right, it should be less than or equals to r, right? So x should be less than or equals to root r. So, and r is order of 10 to the power 9. This is given in the problem. So x must also be less than or equals to root of 10 to the power 9. So here for this case, for every k greater than or equals to 2, what we are going to do is we are going to brute force on the values of the perfect power of k. That is, we are going to brute force for, we will take x equals to 1, right, and x equals to 1 2 3 up to some, let's say, x, and this x we will keep on checking, let's say. So what we are going to do is we are going to iterate over values of x such that x to the power k lies between l and r. Okay, this we can do. We can iterate over values of x because x will always be less than or equals to root of 10 to the power 9, and root of 10 to the power 9 is solvable in uh, less than or equals to 1 second. Okay, so our solution will work here. So let's implement this solution. First of all, let's check this condition. If k is less than or equals to 1, in this case, if k equals to 1, k can't be 0, right? Okay, so if k equals to 1, then we will simply return the total number of integers between l and r. Otherwise we will count. So we will iterate over values of x equals to 0, x. Let's also make a function to calculate power of an integer. X to the power k. While k is greater than 0, simply we can do this k minus minus return rs. Okay, so here we will iterate over values of x until power of x to the power k is less than or equals to r. Okay, here we will check if power of x to the power k, this is greater than or equals to l, then we will increment our answer variable, and at the end we will simply return the answer. For first sample test case, output is 2. Okay, for second the output is 3. Okay, so let's submit it. Great, so it worked. Let's move to the next problem. Before moving to the next problem, if we say the time complexity of this solution, the time complexity of this solution is, for case k equals to 1, the time complexity is order of 1. If we see the time complexity of overall solution, then it is x to the power k, right? So the time complexity for this will be or r to the power 1 by k. This is the time complexity for our overall solution. And there will also be a multiplication factor of k, because for each iteration we are also calculating the power, and this is order of k. So our final time complexity is order of k into r to the power 1 by k. Let's move to the third problem. Largest local values in a matrix. Okay, so you are given an n cross m integer matrix containing non-negative integers. A non-zero cell, row, column checks the cells near it as follows. So there is an integer in this coordinate. Consider every cell x rows and x columns of r, column. Okay. Ignore cells that are outside of the matrix and ignore the cells where both the distances are exactly x. The cell row, column is a local maximum if it is non-zero and no considered cell has a value greater than or equals to x. Return the integer denoting the number of local maximum in a matrix. Okay, so let's see the constraints here. N is order of 200, m is also order of 200, and the values inside the matrix are also order of 200. So they are expecting a solution in n cross m into n or n cross m into m, right? Let's see how we can solve this. So first, to try to understand the problem, we need to calculate the total number of local maximum. So for a particular integer, so for a particular cell, the number of cells near it are x rows above, x rows down, x columns left, x columns right. Okay, and we do not need to consider where the distance is x cross x. These four will be ignored. Okay, so and also we need to calculate the maximum value for all of this grid, right, where the distance is exactly x, less than or equals to x. Okay, so we need to calculate the maximum value. Okay, so we cannot iterate over, for each cell we cannot iterate over all of the cells within a distance of x, because it will take n square m square time, and it's not possible to pass into this solution. So what we can do is, we can, for each cell we can only iterate for each row or for each column, right? So why don't we pre-compute the maximum values for each row between two coordinates? So what I'm saying is, let's calculate the max. First of all, the values of n and m are matrix dot size m equals to matrix of 0 dot size. So let's calculate vector of int max row, max for row. So this is n. For each row we are going to calculate vector of int m comma vector of m. So let me state what I am going to store in this vector. So for each row I am going to calculate, for each row I am going to calculate the maximum value between column j and k, right? This will store maximum value over all cells in row I between columns j and k. Okay, let's first pre-compute this matrix. Iterate over all of the rows. Now iterate over the columns. Let's define a max value. Matrix of I comma j, and iterate over k equals to j to k less than m, k plus plus max matrix of I comma k, max over row of I comma j comma k equals to mx. Okay, so this is good. Now also create a matrix. This is this we will be able to get 4 rows, and here also. Okay, great. So now we have calculated this max over each row between any 2 columns. Now let's solve the original problem. Okay, let's keep answer variable and iterate over all of the cells. Okay, so currently we are at the cell I comma j. Now we need to we need to find the maximum value. So one thing is there, for this row comma column to be local maximum, its value should be non-zero. So first of all check if matrix I of j continue, it can't be a local maximum. The another thing we need to check is its value must be greater than or equals to all of the near cells, right? Near cells. So let's iterate over all of the rows which are near. So row equals to I minus maximum of 0 comma I minus x. Okay, x is the value of this matrix. Okay, x is matrix of ij. R should be less than or equals to minimum of n minus 1 comma I plus x. Okay, and now here comes so now for each row we need to see the two columns. So if r equals to I minus x or r equals to I plus x, in this case our range of columns will be this. This will be minus let's also take variable max value, that is 0. Max equals to maximum of mx comma max over row. We are calculating for row r. Now the range will be for row r equals to I minus x and I plus x. The range of values of columns will be, it will be j minus x plus 1 and j plus x minus 1. Okay, otherwise for all other cases the range for columns will be j minus x and j plus x. Okay, at the end, if mx is less than or equals to x, in this case this is a local maximum. Increase the answer, return the answer. There is another thing we need to check here. This value should not be out of bounds of columns. So let's make it inbound maximum of 0 comma this, and this should be minimum of n minus 1 comma this. Also make this inbound. Let's try out this solution. Output is 1 for the second sample test case. Output is 1 for the third sample test case. Output is 5. Okay, let's submit it. Great, so it worked. Let's move towards problem 4. Smallest unique subarray. You are given an integer array nums. Find the minimum length of your subarray which is not identical to any other subarray in nums. Okay. Return an integer denoting minimum possible length of such a subarray. A subarray is a contiguous non-empty sequence of elements within an array. Two subarrays are considered identical if they have the same length and the same elements in corresponding positions. Okay, so our problem is let's see the constants. 10 to the power 5, 10 to the power 5. So solution is expecting us to solve this problem in order of n or n log n. Okay, so the to understand the problem is we are given an integers, and integer is of the range 10 to power 5, and we need to find the minimum length of a subarray which is such that there does not exist any other subarray identical to this subarray. Okay, so we need to find the unique subarray of minimum length in the array nums. Okay, as we need to solve it in n log n time, so let's say for if we solve this problem for the using the brute force solution, what we can do is we can iterate over each subarray, right? Each subarray between elements between the indices L to R, take this subarray, right? Calculate the hash of this subarray. Okay, let's say the hash is hash, and store it inside a map, an ordered map, let's say, and with its count. Okay, and also store the length. Okay, so we are going to store two things in a map, hash comma length, right? So we need to store this pair and its corresponding count in map, right? So we can create an ordered, okay, let's make a ordered or unordered. So we will make a map. Unordered I think will not support this complex data structure, so we can create a map and insert these values in the map. And finally, after iterating over all of the subarrays of this original array, what we will see is if there is any subarray whose count is 1, right? This count is 1. Then for all of the subarrays whose count is 1, we will choose the minimum length, right? And return the answer, right? Minimum length. This will be our answer, iterating over all of the elements of this map whose count is 1. But this will involve the time complexity of order of n square log n, but we can only afford time complexity of order of n log n or order of n. So let's try to optimize this problem. There is a standard technique which is that is rolling hash. Okay, rolling hash over the strings. So this is a simple and standard approach. So here what we can do is, so think of it something like this. If there exists a subarray, okay, from L to R of length let's say L and Th, and this is of the minimum length. So let's say or don't think of the minimum length right now. So let's say there is a subarray of L to R, okay, and its hash is unique, right? Means its hash is unique. Then can we say can we say this thing that there must exist a subarray of length L length plus 1 whose hash is also unique? Can we say this? Yes, this is true. We can, the reason is, let's say we can take the previous subarray itself and add one of the uh, also add one of the adjacent characters. Let's say this one, r plus 1, r plus 1th character. Then also its hash is going to be unique, because if this subarray is unique, then taking one of the adjacent characters is also going to be unique subarray. So we can apply binary search over values of length of subarray, right? And for each value, let's say we apply binary search for L equals to 0 to R equals to n, means L equals to 1 to R equals to n. Okay, apply binary search over this, and let's say for each mid over the binary search, what we are going to check is if there exists a subarray whose length is mid and its hash is unique. Okay, now how to check, or now our problem remains is how to check this. How to check if there exists a subarray of length mid and its hash is unique. If let's say we have implemented a function, okay, and if this is true, there exists, then what we will do is we will replace r with mid and again apply binary search. If this does not exist, this subarray does not exist of length mid, then what we'll do is we will replace r with mid, L with mid, and then again apply binary search over mid to n. So this is simple, everyone knows this. Now how to calculate this problem, how to solve this problem? For a given length L, we need to find if there exists a subarray whose length is L and its hash is unique. For this we have a standard algorithm which is known as rolling hash. Okay, how do we apply this is we will keep a sliding window, right? For each of the indices, let's say up to n, we will keep a sliding window of length L, and we will calculate the hash for this window, right? And we'll keep on inserting the hash in an unordered map, right? And at the end we will check if there exists a hash whose count is 1. If there exists a hash whose count is 1, then we will return true, otherwise we will return false. Okay, now to see the actual implementation, how we are going to calculate the hash, let's implement this solution of rolling hash. Okay, so first of all the size is this, and let's calculate the power of 10. Okay, and also take modulo function. and we will take this prime number 10 to the power 9 plus 7. Power of 10 0, 10 to the power 0 is 1. Power of 10 to the power I equals to 10 to the power I minus 1 into 10. Now implement the rolling hash. So here we will be given a length L, let's say L, okay, so length L, and we need to check if there exists a subarray whose hash is unique and its length is L. So we'll keep an unordered main, okay, and take a hash function for the sliding window. Okay, do we need anything else? No, I think so. And also take the sliding window so our sliding window is between I to j. So as we have moved to an index I, add the hash of this index. Okay, and if I minus j plus 1 is greater than L, in this case we are going to move the index I one position right, and while moving one position right we also need to make sure that we remove the hash of the index I. How we are going to do this? This we are going to like this: hash equals to hash minus the contribution of the ith index into the hash. What is its contribution? Its contribution is 10 to the power L into this index, sorry, j. We need to subtract the contribution of jth index from this hash. So this is how we can do this: 10 to the power L into nums of j mod, okay, hash equals to hash plus mod. So why we did this thing? We did this because hash from this hash can be a negative value, so to make it positive we added mod and took its mod again. Also make it long such that integer overflow does not occur. Okay, if I minus j plus 1 equals to L, in this case we have a substring of length L and we are going to add its hash into the hash map, or simply call it map. We will increment its counter by 1. At the end we are going to iterate over this map. Count, if count equals to 1 we are just going to return true, otherwise return false. If we are not able to get any hash whose count is 1, then our answer will be false. Now implement the binary search here. it is true, then we are going to left shift R, otherwise we are going to right shift L, and our answer will be value of R. Let's try to run the solution. Unordered, let's correct its spelling. For auto mid, this will be an integer. So for first test case, its output is 3 and we are having output as 1. Why is it so? We made a mistake. Let's debug our solution. This we have calculated correct. Map, we took a map, iterated over all of so for index I. Oh, so here we also need to increment the value of G also. We missed it. Let's again run. First sample answer is 3. For second sample answer is 1. For third sample answer should be 2. Okay, let's submit it. Great, so this was it for this video. If you have any doubts related to these solutions or in general regarding this contest, you may comment. Let's meet in the next video. Thank you.